Hey, welcome back to Numerical Analysis. So, I've been doing my damnedest to keep up with everything lately, just with grant proposals to fund my own students and getting papers out there, and trying to record for my graduate course and then doing it for this course. It is tremendously stressful with roughly about 3 days a week to work. My wife does her best to give me as much time as she can, but she has her own job, and so it's on me to try to get everything done in like half the time I used to. So I do apologize for all that, and yeah, let's go ahead and talk about the lecture today. There will be the second project I'll be announcing today, or yesterday, depending on when I get this lecture all put together this week. Looking at it, it should be pretty fun, and it's more or less a direct application of the things I'm already giving you. So there's not a whole lot of creativity in there other than just plugging in the function correctly. Let's talk about what we're doing today. So in the lecture today, it's going to be the first stepwise method for computing the solution to an initial value problem. A differential equation. An initial value problem is basically a differential equation plus a constraint, right? Sorry, just ate dinner. And ultimately, what we want to do is we want to have a way to resolve that. Picard iteration is a great way to do it. It is sort of the first attempt that anybody does for problems of this sort, because basically to prove that the existence and uniqueness of a problem really comes down to coming up with an iterative method that is contractive, which is what ultimately gives you a Picard formula. And so then you can just try it out. It works reasonably well. But in truth, though, there's some difficulty in actually computing integrals, and there might be a lot of approximations inside of an approximation, and that will cascade into bigger problems as you go forward. So so other methods are often employed, and one of these methods is Eulers Method. This is a really early method in doing numerical, integration and things like that. And it's something you could really kind of guess if I asked you to do it yourself. So I'm going to go through today and prove both the local and global error bounds for Eulers Method, and I'm going to see if I can also squeeze in doing the implicit Eulers Method. This is not the best way to go about this. There are definitely better methods out there, and so the next lecture I'm going to talk about Runge-Kutta, and then that'll round out pretty much numerical analysis at this point. Then the rest of the lectures will really be committed to either extra stuff to show you how all of this gets sort of slammed together, and then in other ways, we're just going to talk about a lot of MATLAB code, and so maybe I'll do a nightly thing. Oh, I'm so tired. Oh, it's gotta be my bedtime. Anyway, so yeah, that's what we're doing today. Tune in, and Eulers Method is piece cake, so hope you like it.
Okay, so let's go ahead and get started. So today we're talking about Eulers Method for solving initial value problems. Okay, so this we're actually going to be referring to Burden and Fair's text, 9th edition. This is numerical analysis. Okay, So, so this is their section 5.2 for all this. So what we're trying to resolve is we have some sort of differential equation, dy dt is equal to f of t comma y for t inside of some interval a, b, and where we declare that y at the left end point is equal to some point alpha, some number alpha. So essentially, we know we have a differential equation, and we're starting, well, not necessarily at 0, but we'll just say at a, we're starting here at y of a is equal to alpha. You can't read that at all, can you? We'll say y of a is equal to alpha. And then the idea is that, we know that we are, trying to make a guess at, say, the true solution here, where this y of t obeys this differential equation, right? But the issue is that y of t isn't always easy to get at. So y of t is not always feasible to find, say, continuously or exactly. Find exactly. And so this motivates numerical approximations. And the numerical approximation that we looked at last time was using Picard's iteration, where we just continuously applied this iterative formula, and we saw that it can work in some cases. Picard's iteration isn't the most reliable way to go about it, and so Euler's method is sort of the beginning of these sort of step-sized methods for solving initial value problems. Euler's method itself actually turns out not to have a very good error bound, but it does have an error bound that we can express. And there are ways to make it smaller, theoretically, but computationally we'll find that actually they don't work as well as claimed. But this allows us to start a process of discussing these sort of procedures for solving initial value problems, and eventually we'll get into talking about something called run-and-kata, and hopefully we'll be able to do that next lecture. So what we're going to do instead of doing this is that we're going to select a handful of points, and so it's going to be, say, so we have T0 is going to be A, T1 being this point, T2 being this point, some points inside of here, Tn capital N minus 1, and then T capital N at B. And so then we're basically going to try to come up with some, hopefully we can get exactly what the value is going to be on the curve, and then we'll interpolate between those points using any interpolation method we want. Usually, though, we just use a piecewise linear interpolation, so just connecting the dots. Now, in actual truth, we're never going to be exactly on the curve. Each one of these points is going to contribute some amount of error. So depending on how big changes the dynamics make, so we can end up having something more like this, where we have something that looks kind of like the curve, but is sort of off a bit. It will always be able to match exactly the initial point because that is actually given in the problem. But the subsequent points, there's no guarantees. And we'll see that this error bound grows exponentially, or the bound that we can get is sort of an exponential bound, which isn't really great. In practice, we tend to be a lot closer than the exponential bound that we're going to see, but theoretically it's harder to get anything better than that. So then how are we going to make these estimations? So what we're going to do is first we simplify the problem, and we're going to say that Ti is equal to A plus IH for some H say bigger than 0. So we'll choose it to be small, but yeah, we'll have a fixed step size. And so this is called the step size for the problem. And then if we can derive Euler's method very quickly, and the way that Burden takes it, the approach is to use Taylor's formula. And so following Burden, we can see that y of ti plus 1 can be written as y of ti plus ti plus 1 minus ti times y prime at ti plus some error term, ti plus 1 minus ti squared divided by 2 factorial, but that's just 2, times y double prime at some point ci, right? So this is the start of our initial guesses. So basically, if we start at yti, so even here at our initial point, then it says that, basically if we just use this, we can get some decent approximation of where we should end up next. We're hoping we end up here, but maybe it won't be quite there. And we end up having this guy contributing to our error formula. So, but how do you find y prime? Well, because we don't even know y. Well, it turns out y satisfies this differential equation. So in here I can write this. I get y of ti plus 1 is equal to y of ti plus ti plus 1 minus ti times f of ti comma y of ti plus our error term y of ti plus 1 minus ti squared divided by 2 times y double prime xci. Okay. So, and then we can simplify it even further because we know that the difference between these two guys should just be h. So then we get this. So we have y of ti plus 1 is equal to y of ti plus h times f of ti y of ti plus ti plus 1 minus ti squared divided by 2 times y double prime xci. Okay, so what do we have at this point? Well, this guy is more or less going to form our Euler's method. We can get a guess at what this guy is by only using this portion and ignoring the remainder formula. Eventually, we're going to see that you can find a bound for the remainder formula in terms of both the derivative, the differential equation, and its derivatives. But as far as we're concerned, this is the bulk of what we care about, this little chunk here. And you can expand and do further other Taylor methods in trying to connect this stuff. And so this turns out to be sort of an exemplar method of all of this. Okay, so then how do we get our approximations? So, what is Euler's method? Okay, so what we're going to see is that we're going to have this sequence. So Euler's method produces a sequence of real numbers that serve as estimates of these terms, y of t naught, y of t1, all the way up to y of tn. Remember, t naught is a and tn is b. So, and what are these real numbers? Well, these are, say, w naught, w1, all the way up to wn following Burden. And so, how do we define them? Well, we set w naught is equal to alpha, so we get a perfect approximation of y of t naught. So, in parentheses, I say this is the same as y of t naught, which is the same as y of a. Because the initial value problem, part of the initial value problem is that the initial point is given. Okay, so then how we make further ones? Well, if I want to go from yi to yi plus 1, I get yi plus 1 is equal to or say wi plus 1 is equal to wi plus h times f of ti comma wi. Right, and this is true for each I going from, say, 0, 1 up to capital N minus 1. Okay, so yeah, so I mean, just a quick example. Again, following, this is an example coming out of Burton. If we take a look at, so we will use Eulers Method to approximate solution to y prime is equal to y minus t squared plus 1 for 0 less than or equal to t less than or equal to 2, and y of 0 is equal to 0.5, right? And so we care about what is the value so approximate solution to this at t is equal to 2, and with step size h is equal to 0.5. Okay, so just copy this. We'll go to the next page. Okay, so the setup here is fairly straightforward, and I'll walk you through the first one, but the rest of it just really kind of takes calculators, as you can guess. But let's see how far we can get without a calculator. So what I'm going to do is I'm going to say, so if we just take a look at the problem itself, we know that y of 0 is at 0.5. So say this is 0.5, this is 1, this is 1.5, 2, 2.53, so 0.5, 1, 2, 1, 1.5, 2, etc. And so we're told that our initial point is here. Boop. And yeah, so we want to be able to get, and our goal is to get over here at 2. And our step size is 0.5. So we don't know exactly where on this line our solution is going to be, and so that's what we're trying to estimate. But in order to get to here, we need to go through and figure out all these other points. So how do we figure them out? Well, we know W naught is already 0.5, and then W1 has to be W naught plus 0.5 times f at say t0 comma w0, right? So we use the current information that we have in order to make a guess at the next one. So so then what we end up getting is, well, we have 0.5 plus 0.5 again times f of t naught, but t naught is just 0, and we know that this is 0.5, so we can go ahead and plug these guys in. All right, so this is the equation that we're plugging it into, and so we're going to have 0.5 minus 0 squared plus 1. Well, this itself is going to be, say, 1/2 plus 1/2 times 1/2 minus 0 plus 1, right? And so we can work this out. It's going to be 1/2 plus 1/2. It's going to be 3/2. It's 1/2 plus 3/4. And so that is 2/4 plus 3/4. That's 5/4. So 1.25. So that puts us, our next point, roughly here. Okay. And so this is 1.25. Sorry for the bump. Okay, so then we can continue. We have now figured out, say, 0.5 comma 1.25, and now we want the next point. So we just do the same algorithm. So W2 now is equal to W1 plus our step size, 0.5, times f at, now we're going to be at 0.5, comma 1.25. And so plugging those in, we get, say, 5 quarters from W1, plus, say, 1/2 from our step size. And then, and after that, we have putting in for y, it's going to be 5 quarters minus 1/2 squared, so it's going to be 1/4, and then plus 1. All right. This is still something we can do. So 5 quarters plus 1/2. So 5 minus 1/4 plus 1. So that's going to be 1 plus 1, that's 2. And so it's going to be 2. And so now we have 5 quarters plus 1, essentially. And so it's going to be 9 quarters. Okay, 9 quarters is 2.25, if I'm not mistaken. And yes, it agrees with what they have, so good. All right, so 2.25. All right, so it's growing pretty quick, right? Okay, there we go. Yep, so now let's go ahead and find the next point. My guess is that this is going to be growing exponentially fast. My intuition really is coming from this. Y prime is equal to y is essentially the exponential function. And if you subtract something that's only time dependent, t squared, ultimately you're basically going to be having the exponential function minus t squared, and t squared is almost nothing there. So so maybe my bounds here for the scale it might be a little suspect, so we might have to put a point up here eventually. So let's take a look at W3 and see what we got. So W3 is equal to so 9 quarters plus 0.5. Now f, the t1, we're at putting in t2 here, right? So it's W3, t2 goes in, and t2 is 1. And so then W1 now goes in for y, and that is, or sorry, W2 goes in for y, and that was 9 quarters. And so put everything together, so we're going to have 9 quarters plus 1/2 times 9 quarters again, because that's what goes in for y, minus 1 squared, and so that is just 1 plus 1. So again, easy enough to do. This is 9 quarters plus 1/2 times 9 quarters, and so it's going to be 9 quarters plus 9/8, and so that is going to be 18/8 plus 9/8 is 27/8, and so 8 goes into 27 3 times, so that is going to be 3 point something, and according to them is 3.375. So that is what, somewhere up here. I don't know, just gonna put it there. Okay, so let's keep going. We got one more to do. We can do this. We're adults. We've done math. So we get W4 is equal to W3 plus 0.5 times f of 1.5 comma 27/8. Oh man, I don't know if I want to be an adult. 27/8 can go in here. Alright, so 27/8 plus 1/2 times 27/8 plus minus t squared, so 1.5 squared, so what is 1.5? That is 3 halves squared, so that's 9 quarters plus 1. Okay. So let's figure this out. So we had 27/8 plus 1/2, and then 27 over 8 minus 9 over 4, that is going to be 18 over 8 from the 9 over 4. So that's going to be 9/8 here. Plus 1 was 9/8 plus 1. That is 17/8. Okay, so that is going to be 27/8 plus 17 over 16. And 27/8 is going to be something over 16. So it double 27 or 56, 54. So there we go. So we get 54 plus 17, and that is going to be 71 over 16, I think. Yeah, I think it's right. Okay, so there we go. Piece of cake. Okay, so I think that it's going to be a little bit more than 3 again, and yeah, indeed. Is that actually everything right? I think I did. No, you can double check that. But what they put in the book is that this is about 4.5. So, so coming from Burden, they wrote 4.4375. So this is Burden, and so that puts it clear up here. So much bigger. Okay. Anyway, so that gives us our approximation that we were looking for, and so the guess is that y of 2 should be equal to roughly 4.4375. So we got. Now I'm just curious, did that even come close? I'm gonna pull up a calculator on my computer somewhere. All right, so let's see. 71 divided by 16 is 4.375. Bam! That's right. Okay, so yeah, I actually did arithmetic correct throughout that whole thing. This is it's a minor miracle, and I should probably dance if I probably bumped the microphone. Okay, so there you go. That is Euler's method and an application of it. That's yeah, pretty much what you can expect, and it's not too bad. Now, what we really want to know now is if we can come up with sort of error bound. So how do we know? I mean, so we made this guess for what y of 2 should be, but can we get some sort of like error bounds like what we like out of any numerical method? And so this next step is where it graduates us from, say, just plain differential equations, where we learned Euler's method and probably like the first week. And now this graduates us to actually come up with a way of demonstrating that Euler's method actually works. It doesn't, not really, but theoretically it does. In practice, the idea is going to be that you end up having a lot of round-off errors, and it's going to screw things up. But in general, just like we saw with a lot of, so in principle, like what we saw with a lot of numerical techniques in the past, we can improve the performance of a method by decreasing things like the step size or the distance between two samples. And so just like with interpolation methods, if we had a whole lot of interpolation sites, we expected the overall approximation to improve in some certain circumstances, like when the function is, say, infinitely differentiable with a bounded derivative. Now, in this case, instead of having interpolation sites, we actually have this step size. And so as the step size shrinks, then we, in principle, believe that this should contribute to a better approximation. Now, theoretically, we're going to see that this exactly happens, and it gives us a method that gives us a global error bound of big O of h, which we're going to find for Euler's method. And we already know that big O of h is not that great. But there's a second issue that ends up coming up here, and and that is going to be some sort of accumulation that is going to end up happening. So theoretically, we can get a big O of H convergence, but computationally, we're going to find that this can lead to a lot of errors, because for very, very small H, that means we need to do a lot of calculations. And every time we do a calculation, we end up having some sort of round-off error. So we have finite precision in our computers, and so then therefore, like, at some point we have to make a rounding decision. And so these rounding decisions can actually have an accumulative effect that'll end up, destroying your result. So what you'll see is that on a computer, you'll start to decrease H. You'll see that the error starts to get smaller and smaller and smaller, but then after a certain point, the error starts growing again because of all these round-off errors they're accumulating. So because Euler's method demands that you have such a small thing, because it's only big of H, researchers usually use other methods, like and the modal one that most people use is a Runge-Kutta of 4, and we'll talk about that subsequently. But for today, the nice thing about Euler's method is that we can get a really nice error bound just from a little bit of calculus and discussion. So there's going to be 2 or 3 lemmas that are coming out here from Burden, and then we'll use these and spin them up into a full theorem for an error bound for Euler's method. So let's go ahead and do this. Okay, so one thing I should note, though, is that there's a difference between a global and a local error bound for a lot of these initial value problems. So as far as our local error, so like if we only took one step and we were perfect on the last one, then the error that is going to end up coming through here is going to be big O of H squared. And so then you might immediately object to my claim that we're going to end up having big O of H thing, because you're like, oh, I see big O of H squared here. But you keep in mind that basically what we're going to do is we're going to have to sum up over all of those individual bits, and so we're going to have a sum of a whole bunch of H squareds. And so then, just like integration, so then just like we saw with the integration theory, we're going to have to end up absorbing one of those H's away in order to handle another term that's going to be growing larger. And so in order to get that concrete bound, we have to sacrifice one of these H's that come from our local terms. And then that ends up leaving a global error of big O of H. So I'm just going to put big O of H so we know what it is, but then we'll follow Burden through his analysis. So this is Lemma 5.7 out of Burden and Fair's numerical analysis book, 9th edition, and it says that for all x greater than or equal to -1 and any positive n, we have 0 less than or equal to 1 plus x to the m less than or equal to e to the mx. All right, and so let's go ahead and prove this. This is a really fundamental result and bound that's used a lot in analysis, and so we can go ahead and use it here. And so basically what we're going to do is we're going to use Taylor's theorem on e to the x, and then we're just going to be smart Alex and exponentiate. So basically what we see is that we have e to the x is equal to 1 plus x plus 1/2 of x squared times, I'm just going to put e to the x is going to be, say, g of x here, just to be clear what's going on, times e to the, g double prime xc for some c, but we know the derivative of e to the x is just e to the x, so e to the xc. So just shaving this off, because this is all positive, what we end up finding is that this gives us 0 is less than or equal to 1 plus x, and sorry, let's see. So 0 is less than or equal to 1 plus x is less than e to the x, because we just shave off this positive term, and that's what it gives that to us. Now, here we go. How do I get from this to the final answer? Exponentiate everything. So that means that 0 is less than or equal to 1 plus x to the m less than or equal to e to the m times x, right? And done. So that's a really simple bound to get, but it turns out to be really handy in the future. All right, so Lemma 5.7, done. All right, so this next one takes a little bit more work. And this is really going to be the bulk of the work that goes into Euler's method. So what we're going to have, so this one is Lemma 5.8, and it says that if t and s are positive real numbers, and say ai going from 0 to k is a sequence satisfying this. So we have a naught is bigger than or equal to minus t over s, and we have that ai plus 1 is less than or equal to 1 plus s times ai plus t for each I going from 0 to 1 to 2 all the way up to k minus 1. Okay, so then what happens? So then we have this ai plus 1 is less than or equal to e to the I plus 1 times s times a naught plus t over s minus t over s, right? And that's what we're going to have. Now, how does this relate to what we're talking about? Well, generally speaking, we're thinking of these AIs as our WIs. And, well, really, it's going to be, so it's going to be related to our WIs. And so then we're going to use this in order to establish a cumulative error bound. And so I think AIs actually end up being y of ti minus w of I, but we'll see when we get there. We have one more theorem to get through after this, and then that'll be so the next theorem is exactly the bound that we're talking about, and it is, I was right, AI is ultimately going to be so thinking AI is going to be y of ti minus wi, and so this is where this lemma is going to end up coming into our analysis. But this will give us a nice one line attack on this one problem. So we basically are going, in the next theorem, we're going to show that this satisfies this, and then we'll be golden. And the demonstration that it satisfies that comes through using the Taylor series method. Okay, so let's go ahead and jump into the proof of Lemma 5.8 from the 9th edition of Bird and Fairs. Okay, so start here. Proof. Okay, so the proof is actually not too bad. I mean, we just more or less apply this recursive inequality over and over again, and we end up at our result. So what we're going to do is we're just going to basically start at ai plus 1, and we know just by our hypothesis that this is less than 1 plus s times ai plus t. And already this is starting to look a little bit like our last theorem, something that came out of our last lemma. And we have 1 plus s. Now s is positive, so it's definitely bigger than negative 1, which is the requirements for the last one. And you're going to see this we're going to have an accumulation of 1 plus s's as we go and keep applying this. So then what we can do is you just take ai and you replace it with ai minus 1. And so this is going to be less than or equal to 1 plus s times 1 plus s times ai minus 1 plus t. And then we have plus t here. So putting these together, this is actually equal to 1 plus s squared times ai minus 1. And then we have we have a 1 plus s plus 1, and this times t. So this applies to here and distributes, and so then etc. And so then I can now take ai minus 1 and do the same routine, and going and collecting everything that is going to give me something else. So let me change color so we can recognize it. So this is less than or equal to 1 plus s cubed ai minus 2, and then what's going to be left over here is going to be 1 plus s squared plus 1 plus s plus 1 times t. And so then you keep going and you can sort of extrapolate a pattern. So we drop down, so each time we drop down by 1, we end up with another power and 1 plus s, and so yeah, so that's nice. So then ultimately, if I'm going to get down to a naught, which was our initial point, then let's see. So when I went from ai plus 1 down to ai minus 2, that was a drop of 3, and that exponent went up here. So now that means we're doing a drop of I plus 1. So that means we're going to have 1 plus s to the I plus first. And over here, we're going to have 1 plus s to the I plus 1 plus s to the I minus 1 plus all the way down until we get to 1 plus s plus 1 times t. Okay. And so we've basically done a whole bunch of these inequalities over and over again until we got down to the very bottom. Now we could have taken the time and instead of putting ellipses, prove this by induction, which some mathematicians would actually very much prefer. But in this case, I think this is pretty clear. Okay, so now what do we do next? Well, what you can do is you can notice that this is a geometric sequence. It's not a geometric series, which would require then that 1 plus s is less than 1 in order to use the formula. But in our setting, since this is a finite sum, there's a finite geometric sequence sum, if you remember or not. And so we can go ahead and bring that over here. So I'll change this back to blue. And so this gives us ai plus 1 is going to be less than or equal to 1 plus s to the I plus 1 times a naught plus, now we have, let's see, so we're summing all these other guys. And so if you just sort of recall, if I have the sum of, say, picking some nice number, r to the k going from, say, 0 up to n, this ultimately becomes 1 minus r to the n plus 1 divided by 1 minus r. So, or if I want, I can also change the order of both of them on top and bottom, so that would work out too. And so then going with that second formula, that's what Burden ultimately uses, we get this. So this is going to be the sum. It becomes 1 plus s raised to the I plus first, because we end on I, and then we're going to subtract 1 and then divide by 1 plus s minus 1. So ultimately this gives us an s plus 1 to the I plus 1 minus 1 divided by s. This all times t. Okay. And so then I can go ahead and regroup things. So I am going to have, I have a s plus 1 to the I plus 1 here, and s plus 1 to the I plus 1 there. I'm going to shave off this, and I'm going to factor out an a0. And so let's go ahead and do all that at once if we can. So we get 1 plus s to the I plus first power. And what were these guys attached to? Well, this was attached to a0 over here, and the other one was attached to t over s. Now, the other one is going to be minus t over s here. So, and I think that's the right formula, if I see. Yeah. And so yeah, so now how do we wrap up? Well, we know that 1 plus s to the I plus first power is less than e to the s. So this might seem dramatic, but we get this. I plus 1 to the s times a0 plus t over s minus t over s. And there we go. That is the end of that lemma. Okay, so now we have proven 2 lemmas that will lead into our theorem, and so then we can now talk about theorem 5.9 out of Burden, and this is what we get. So we say, suppose f is continuous and satisfies the Lipschitz condition with constant L on D, which is this region ty, where we have, say, t living between a, b, and y is a real number. Okay, oops, sorry. So Lipschitz condition is basically what I'm saying is that f of t, let me just double check that this is exactly the condition that we're talking about. Yep. Trying to figure out which portion they're using the, yeah, okay, yeah, that's right. So basically what we're saying is ty minus f of t comma something else, z, is going to be less than or equal to L of y minus z. All right, so this is the Lipschitz condition. So one thing you should note is that if it is actually differentiable, continuously differentiable in the second variable with bounded derivative, then it satisfies a Lipschitz condition. The Lipschitz condition actually doesn't require that the function itself is differentiable, and so so this is a little bit of a weaker condition than what you would require if you have something like differentiable. When I say weaker, that actually improves the theorem because we're putting a less of a restriction on our functions. But in practice, we're always going to have differentiable f for any point in this class. And even for general numerical methods, you rarely can do anything without having some sort of continuity assumption on your dynamics. There are people who do work with discontinuous things, and those kill uniqueness. And so, or things that don't satisfy Lipschitz conditions, and those violate the uniqueness of initial value problems. And so they require a whole other realm of analysis that most mathematicians never even touch. Okay, so then, oh man, there's more to this theorem. So we've only started the beginning of this. So we're supposing that f is continuous and satisfies the Lipschitz condition, which I just told you what it is, and there exists an m bigger than 0 such that y double prime of t in absolute value is less than or equal to m for all t in, say, 0 a to b, and this is where y of t solves y prime is equal to f of t comma y for t in AB with say y of a is equal to alpha. Okay. And now we're going to say let w naught, w1, all the way up to wn be approximation, come from Euler's method. Then what basically we're going to have is we're going to have y of ti then minus wi is going to be less than or equal to h times m over 2l times e to the l ti minus a minus 1. Oh, man. Okay. So here we're implicitly assuming that we have selected a step size h, and that's what we said when it says it comes from Euler's method. That means we had selected an h as in earlier. And then we have these TIs, etc. So TI is going to basically be a plus IH. And so this whole thing becomes IH in here. And yeah. And so basically from lemmas, we've sort of hinted that this is going to come from using lemma 5.8 here. And so basically what we're going to be doing is we're going to be trying to show that this is that this sequence here satisfies the conditions of lemma 5.8. All right, so let's go ahead and get started. Okay, so just to start, when I equals 0, we have y of a is equal to alpha, and we already set w naught is equal to alpha. I mean, that is done. So the fact that so then we automatically satisfy this bound because the left hand side is 0 and the right hand side is positive. So done. So then if we want to build up from there, basically is what we're going to do is we start by looking at Taylor's theorem. So we see that y of ti plus 1 is equal to y of ti plus h times f of ti comma y of ti. This is what we did right in the very beginning, plus h squared over 2 times y double prime of ci. And we already see where we're going to need that bound on the second derivative coming up in here. Okay, and so this holds for I equals 0, 1, 2, all the way up to n minus 1. And then we also have wi plus 1 is equal to wi plus h times f of ti and wi. And this is just straight from the definition. So now what we do is we go ahead and subtract them. So we're going to set yi is equal to y of ti, just for sake of notation. And so then this is what we end up having. So we end up having y of I plus 1 minus wi plus 1 is equal to yi minus wi. So like we have two members of our sequence that we're thinking of. Now this is plus h times these two f's. So we're going to have, oops, oh, I hate when it does that. There we go. F of ti, comma yi, minus f of ti, comma wi. And now we still have this error term lingering around, this h squared over 2 y double prime xci. Okay, so then let's go ahead and put absolute values and everything, use triangle inequality. So hence we have yi plus 1 minus wi plus 1 is less than or equal to yi minus wi plus h times, now here we're going to use that Lipschitz condition. So this is going to be is going to be L times the absolute value of yi minus wi. Again, that's a member of our sequence here. And now we're going to have plus h squared over 2 times y double prime xci But again, I want to get rid of that too. And so we have this into absolute values now, and I'm going to replace this with m. Okay, so great. Now let's do a little bit of factoring, and I think we're almost done. 1 plus h times L times yi minus wi plus h squared over 2 times m. Okay, so now if you squint a little bit, we can see that this is going to be our s term from that one theorem, and this is going to end up being t. And so we can just jump at the conclusion here, and this is what we find. So we have yi plus 1 minus wi plus 1, this is coming straight out of Lemma 5.8, is less than or equal to e to the I plus 1 times hl times y naught minus w naught plus h squared m over l 2hl and minus h squared m over 2hl. Okay, so this is pretty close to done. If you take a look at the theorem, more or less this is what we have, but notice that in this equation we don't have y naught and w naught. But that's pretty simple. Y naught is equal to w naught, so guess what? This is 0. So then ultimately what we end up having is we have e to the I plus 1 times hl, and then I can just sort of subtract, I can factor out this other term, h squared m over 2h over, well, here, yeah, h m over 2l now. And now we can see this is equal to big O of h, because we have this h here. So as h shrinks, this is getting smaller. And so in principle, we should be doing okay. Now, keep in mind that this up here is actually ti minus a with this I plus 1h, because we really don't want that growing too much. We don't want it growing exponential here. So I plus 1 is actually influenced by h, and so we can go ahead and replace that. So instead here, I'm just going to put ti minus a. There we go. And now we know that this is bounded by b minus a. So, good. So now we have a term that is bounded on left-hand side. We have h, and these are just fixed constants. So yeah. So that's where we get the big O of h from. And so I'm going to go ahead and end there. And so yeah. So this is Euler's method. We've demonstrated its convergence, and yeah, that's it. So next time we're going to talk about a different step method for computing a solution to the initial value problem. But this is a very nice example of the sort of things you face with these sort of things. But keep in mind, as your time grows, so here we're just stuck between b minus a, and so that, I mean, we know that's bounded, but if you're looking at longer and longer time horizons, so b minus a getting bigger and bigger, this constant here is going to end up growing exponentially. So your error bound is no longer going to be constrained, but it's going to grow exponentially. And it turns out that you can, some problems you're not actually going to see that. It is just strictly an upper bound. But there are a few example ones where you're going to end up seeing this sort of blow up. So yeah, so this isn't the best, and they're all going to have this sort of term in here, and so the only way we're really going to be able to handle that sort of thing is by finding ways of increasing the powers of h. And as you can guess, Taylor's methods can come up to help resolve that, and other things like that. There's one last thing we should also mention, and that is this bound on the second derivative. We don't have access to it directly, but what we can do is, since we know that y prime is equal to f of t comma y of t, that tells us that if I take the second derivative here, we can use a chain rule, and so we get d by dt of f of t y of t plus the derivative with respect to y of f of t y of t, and then pop out by chain rule the derivative of y, but the derivative of y itself is y of t here. So this is y prime. And so if we can get a bound on these quantities, we're good. And if f is continuously differentiable, and we stick to a compact region, then you're able to actually bound this. And this doesn't actually require knowledge of the actual solution now. If you just need to know over some fixed region of y and t, you can exploit compactness. Okay, so that's where I'm going to end, and thank you for watching.
All right, welcome back. So that is the 101 method, stepwise method for solving a initial value problem. It's it's easy to prove error bounds and convergence, but it's only like big O of h, and and there are much better methods out there. Runge-Kutta, which I'm going to talk about next, is actually a collection of methods, but the Runge-Kutta 4 is the one that's typically used, and they have much higher rates of convergence, and more or less they become the standard that people apply when they are doing a solution to an initial value problem. Just like Simpson's rule is used for integration. And if I remember right, I think Runge-Kutta 4 actually comes from Simpson's rule, but I haven't actually checked that proof yet. So we'll see that next time. In any case, thanks for tuning in, and thank you for being patient with me. All right, take care.